Welcome dear learners. We are continuing Unit 5 Inorganic Chemistry Practical 1 Volumetric Analysis. In the present module we are discussing experiment number 12, that is determination of available chlorine in bleaching powder. The contents of this module are a brief description about bleaching powder, available chlorine in bleaching powder, aim of the present experiment, principle behind the experiment, reagents required for the experiment, the procedure which has 3 parts, preparation of standard potassium dichromate solution, standardization of sodium thiosulfate solution, estimation of bleaching powder, and finally results of the entire experiment. First of all, bleaching powder. Bleaching powder is a very important chemical species which is obtained by passing chlorine gas through dry slaked lime. We can now have a brief discussion on bleaching powder. Bleaching powder, also known as chlorinated lime, is a pale yellowish white powder with a strong smell of chlorine. It is widely used as a disinfectant, bleaching agent and in water treatment. Remember, bleaching powder is highly useful as a disinfectant for the treatment of water. It has bleaching action. Bleaching action is a kind of oxidizing action. Now, the chemical formula of bleaching powder, active component of the bleaching powder is CaOClCl, that is calcium chloride hypochlorite. This is the exact formula of active component of the bleaching powder. The more descriptive chemical formula of all components present in a bleaching powder sample can be represented like this: CaOCl twice, CaCl2, CaOH twice, H2. This is the complete descriptive formula, and the first one is the chemical formula of the active component in bleaching powder. Now, the bleaching powder is prepared by passing chlorine gas over dry slaked lime. Slaked lime is CaOH twice, and the passage of chlorine gas through dry slaked lime is performed at room temperature to obtain the bleaching powder. The reaction responsible for the formation of the bleaching powder is shown here. CaOH twice, that is slaked lime, plus Cl2 produces CaOClCl plus H2O. CaOClCl is the active component of the bleaching powder, that is calcium chloride hypochlorite. Now, available chlorine. Available chlorine in bleaching powder. The aim of the present experiment is to evaluate available chlorine in the bleaching powder or to estimate the chlorine content in bleaching powder. Now the question arises, what is meant by available chlorine? Available chlorine refers to the amount of chlorine that is available for oxidation when bleaching powder is used. It is the amount of chlorine liberated from bleaching powder by the action of dilute acids. So, from this statement it is clear that bleaching powder can liberate chlorine when it reacts with dilute acids. Now, CaOClCl plus 2HCl gives CaCl2 plus Cl2 plus H2O. This is the reaction showing the liberation of chlorine from bleaching powder in the presence of hydrochloric acid. Thus, available chlorine is a measure of this liberated chlorine gas and indicates the strength or purity of the bleaching powder. Higher the liberated chlorine, more will be the quality of the bleaching powder, or its bleaching action will be in very good level. It is usually expressed as percentage by weight of the bleaching powder. That means available chlorine, the available chlorine content in the bleaching powder is generally expressed as a percentage by weight. Now, we are discussing aim of the present experiment. It is very well clear that the aim of the experiment is to estimate the amount of available chlorine in the bleaching powder, and for this experiment you are provided with approximately n by 20 sodium thiosulfate solution and annular potassium dichromate crystals. So, n by 20 sodium thiosulfate solution and Ar K2Cr2O7 are two important reagents you are supplied with to estimate the amount of available chlorine in the given bleaching powder. Now, moving on to the principle behind the estimation of available chlorine. Annular potassium dichromate crystal is a primary standard, and this material is used to prepare a standard solution. By using the standard solution of potassium dichromate, we can estimate sodium thiosulfate, or we can find out the concentration, or we can standardize sodium thiosulfate. In the presence of hydrochloric acid, K2Cr2O7 liberates iodine from a solution of potassium iodide. That is, iodine is liberated from Ki when it is treated with the potassium dichromate in the presence of hydrochloric acid as per this equation. K2Cr2O7 plus 6 Ki plus 14 HCl gives 2 CrCl3 plus 8 KCl plus 7 water molecules plus 3 iodine. It is clear that iodine is liberated during this reaction. You can utilize this liberated iodine for titration with the sodium thiosulfate solution. So, that is the titration procedure involving liberated iodine, and you can call it as iodometric titration. Remember, in this expression, the plus 6 oxidation state of potassium dichromate is just reduced to plus 3 state in CrCl3. So, K2Cr2O7 acts as a good oxidizing agent. You already studied that potassium dichromate in acid medium is a powerful oxidizing agent. Here you can see the presence of hydrochloric acid. So, the reaction is in the acid medium. At the same time, potassium iodide consists of I minus is just oxidized to I2. That is, Ki or potassium iodide acts as a reducing agent, and K2Cr2O7 acts as an oxidizing agent. So, this is simply a redox reaction. Now, the equivalent mass of potassium dichromate, that is the oxidizing agent in this reaction, can be calculated as equivalent mass of an oxidizing agent is equal to molar mass divided by change in oxidation number. By that argument, it is possible to get the equivalent mass of potassium dichromate as 49. The calculation part we already learned in previous modules. Now, the liberated iodine during this reaction can be titrated with the sodium thiosulfate solution. Iodine oxidizes sodium thiosulfate solution to a new compound, that is sodium tetrathionate. This is the reaction responsible for the oxidation of sodium thiosulfate by iodine. 2Na2H2O3 plus I2 produces Na2S4O6, that is sodium tetrathionate, and sodium iodide will also be obtained. Now, since one molecule of Na2H2O3 reacts with one equivalent of iodine, the equivalent mass of sodium thiosulfate is same as its molar mass. Remember, Na2H2O3 is commercially available or available in stable form as Na2H2O3 5H2O, that is sodium thiosulfate pentahydrate. So, for every analysis we are using sodium thiosulfate pentahydrate. So, the molar mass of sodium thiosulfate pentahydrate is calculated as 248.19, and this molar mass is same as the equivalent mass, that is equivalent mass of sodium thiosulfate is taken as 248.19. Now, using the standardized sodium thiosulfate solution, which is standardized by using a standard solution of potassium dichromate in the previous part, the given bleaching powder can be estimated. A definite mass of bleaching powder suspended in water is treated with potassium iodide in acid medium. An equivalent amount of iodine is set free, which is titrated against standardized sodium thiosulfate solution. This is the expression responsible for the liberation of iodine with the help of the active component of the bleaching powder, that is 2CaOClCl plus 4Ki plus 4CS3COOH, that is acetic acid, which is a weak acid which helps the liberation of iodine, gives 2CaCl2 plus 4CS3COOK, that is potassium acetate, plus 2 molecules of water plus 2 molecules of iodine. 2Na2H2O3 plus this liberated iodine gives Na2S4O6 plus 2 molecules of sodium iodide. Now, in both the titrations, that is the standardization part as well as the estimation part, we can use starch as the indicator. At the end point, the blue color changes to colorless. Now we are discussing the reagents required for the present experiment. The reagents required are K2Cr2O7 or potassium dichromate crystals, approximately N by 20 sodium thiosulfate solution, bleaching powder, the given bleaching powder based on which we are performing the estimation of available chlorine, and concentrated hydrochloric acid, 5% potassium iodide solution, starch indicator, starch acts as indicator, and glacial acetic acid is also required for the reaction. Now we are discussing the experimental procedure behind the experiment. The experiment consists of 3 parts I already mentioned, and we are going to the procedural aspects of the first part of the experiment, that is preparation of standard K2Cr2O7 solution. Mass of K2Cr2O7 required to prepare 250 ml of N by 20 solution can be calculated by using the previously very well established expression, that is weight required is equal to VEN divided by 1000. As you know, V represents the volume, that is 250 ml here. E represents equivalent weight of potassium dichromate, that is all equal to 49. N represents normality of the prepared, the solution to be prepared, that is equal to N by 20 or 0.05, and weight required is equal to VEN divided by 1000, that is again equal to 250 into 49 into 0.05 divided by 1000, and you will get the weight as 0.6125 gram. Thus, it means a mass of 0.6125 gram of potassium dichromate made up to 250 ml produces N by 20 or 0.05 normal potassium dichromate solution. Now, roughly weigh out 0.06 gram of AR potassium dichromate and transferred it to a dry weighing bottle. As in the previous case, it is weighed by an electronic balance and the weight is recorded as W1. W1 is the weight of potassium dichromate plus the weighing bottle. The substance is the potassium dichromate weighed in the weighing bottle is now transferred into a 250 ml standard flask through a funnel and made up to the mark, that is made up to 250 ml by using distilled water. Now, the weight of empty weighing bottle is again taken and it is recorded as W2. W1 represents weight of weighing bottle plus potassium dichromate and W2 represents weight of the empty weighing bottle, and the actual weight of potassium dichromate is calculated like this, W2 minus W1, and this weight of potassium dichromate W1 minus W2 is used to find out the concentration of the prepared solution of potassium dichromate by using the expression normality equal to weight per liter divided by equivalent weight. Now, the second part of the experiment, standardization of sodium thiosulfate. Here we are performing a titration between the already prepared standard solution of potassium dichromate with the sodium thiosulfate, and for this purpose we are adopting a conventional titration procedure other than a double burette titration method. For this purpose, 20 ml of the made up potassium dichromate solution is pipetted out into a clean conical flask and add 3 ml of pure concentrated hydrochloric acid. Now add 10 ml of 5% potassium iodide solution and diluted to 100 ml, and the solution is titrated against already given solution of sodium thiosulfate taken in the burette. Now, the addition of sodium thiosulfate is continued until the solution is changed to pale yellow in color. At this color change point, you have to add 2 ml starch solution, and the titration is continued until the blue color changes to green. whenever you are adding the starch solution, a blue color is developed, and you have to continue the titration till that blue color just changes to green color. Now repeat the titration for concordant values. We are now demonstrating the standardization of sodium thiosulfate. the standardization experiment and now entering into the calculation part. The weight of potassium dichromate taken is equal to the difference in weight, that is equal to W1 minus W2. In the present experiment, we go to the weight as 0.62 onto gram. Therefore, weight of potassium dichromate per liter is equal to 0.62 onto multiplied with the 4. And why we have to multiply with the 4 is due to the fact that you are preparing a 250 ml solution. Weight per liter is the weight per 1000 ml. So, you have to multiply with the 4 in order to get the weight per 1000 ml or weight per liter. So, weight per liter is equal to 2.4848 gram. Now, normality of K2Cr2O7 solution will be equal to weight per liter divided by equivalent weight. That is, weight per liter 2.4848 divided by equivalent weight of potassium dichromate 49. You are getting the final concentration of the prepared solution of potassium dichromate as 0.0507 normal. This is the normality of the standard solution of potassium dichromate. Moving on to further calculation, the titer values between the titration of potassium dichromate and sodium thiosulfate can be tabulated like this. K2Cr2O7 against sodium thiosulfate. The volume of potassium dichromate pipetted out during 3 consecutive titrations will be equal to 20 ml, as you can see in the second column of the tabular column. And the burette reading, corresponding burette readings are noted here. And from this chart, it is clear that the concordant value corresponds to the volume of sodium thiosulfate is equal to 20.6 ml. That is, 20.6 ml is the volume of sodium thiosulfate consumed during its titration with the potassium dichromate. Now, from these titer values, we can calculate the normality of sodium thiosulfate solution using the relation, that is the volumetric relation N1V1 equal to N2V2, which is modified as N sodium thiosulfate into V sodium thiosulfate equal to N potassium dichromate into V potassium dichromate for the present experiment. N K2Cr2O7 we already calculated, that is the concentration of the standard solution of the potassium dichromate, that is equal to 0.0507 normal. Volume of potassium dichromate taken is equal to 20 ml. Volume of sodium thiosulfate used in this reaction, that is the concordant value of the titration, which is noted as 20.6 ml, and by proper substitution we will get the normality of the sodium thiosulfate solution as 0.0492 normal. Thus, we have evaluated the concentration of the given sodium thiosulfate solution, or we standardized the sodium thiosulfate solution. With this sodium thiosulfate solution, we are entering into the estimation part. Now, estimation of bleaching powder, that is the last part of the experiment. 1.25 gram of bleaching powder, this is an optimized quantity. 1.25 gram of bleaching powder is accurately weighed in a weighing bottle. It is now transferred to a clean mortar and grounded to thin paste and grounded and made it into a thin paste with the water. The mixture is allowed to settle and the milky suspended liquid poured into 250 ml standard flask. The residues is ground with little more water and the operation is repeated until the whole of the sample has been quantitatively transferred into a standard flask. The mortar and pestle are thoroughly washed and all the washings are transferred to the standard flask and the solution is made up to the volume. Now, the standard flask is shaken well for uniform concentration. Thus, a fixed quantity of bleaching powder is weighed out and made up to a fixed volume in a standard flask. 20 ml of the made up solution in a state of very fine suspension is pipetted out into a 250 ml conical flask. 10 ml of 5% potassium iodide solution is added, followed by 10 ml of glacial acetic acid. The liberated iodine is titrated against standard sodium thiosulfate solution. About 2 ml of freshly prepared starch solution is added when the solution has a pale yellow color and the titration is continued until the blue color just disappears. The titrations are repeated for concordant values. Now we are demonstrating the estimation of bleaching powder over to the experiment. conducted the estimation part and now entering into the calculation part of the experiment. The titer values can be tabulated as follows. The titration is between bleaching powder solution that you already prepared and standardized sodium thiosulfate, and for this purpose bleaching powder solution is pipetted out. Since you are performing the titrations thrice, the volume pipetted out is the same in all three cases, that is equal to 20 ml. The corresponding burette reading which shows the volume of sodium thiosulfate is shown in the last column, and here from the chart it is clear that the concordant value corresponds to the volume of sodium thiosulfate will be equal to 20.1 ml. Now from the titer values we can calculate the normality of chlorine in bleaching powder solution using the relation N1V1 equal to N2V2. N1 stands for normality of bleaching powder solution, V1 stands for volume of bleaching powder solution, N2 is already calculated, that is equal to normality of the sodium thiosulfate which we already standardized, and that is equal to 0.0492 normal, and V2 stands for the volume of sodium thiosulfate used, that is the concordant value of the present titration that we got as 20.1. So on proper substitution we will get N1 equal to N2 V2 divided by V1, which is again equal to 0.0492 multiplied with the 20.1, and the whole thing should be divided with 20. You will get the normality of the bleaching powder solution as 0.0494 normal. Now weight per liter of the chlorine in solution is obtained by the expression weight per liter is equal to normality into equivalent weight. Normality of the solution is equal to 0.0494 normal. Just to multiply with equivalent weight of chlorine, that is equal to 35.5, you will get a final value which is equal to 1.7537 gram per liter. This is the weight per liter of the chlorine in the solution. Now mass of chlorine in the whole of the given solution is calculated by the expression weight per liter divided by 4. Since you are preparing the solution to 250 ml, you have to divide it with the 4. So weight per liter divided by 4, that is equal to 0.4384 gram. That is mass of chlorine in the whole of the given solution. Now mass of bleaching powder already taken. In the present experiment we weighed out some quantity of bleaching powder that is noted as 1.312 gram. So percentage of available chlorine in the solution is equal to mass of chlorine divided by mass of bleaching powder multiplied with 100. That is equal to 0.4384, that is mass of chlorine in the whole of the solution, divided by mass of bleaching powder taken, that is equal to 1.312 gram. Just to multiply with 100 to get it as a percentage, and you will get the value as 33.41%. The final results of the experiment is shown here. The percentage of available chlorine in the given sample of bleaching powder is equal to 33.41%. Thus, we have evaluated available chlorine content in a given sample of bleaching powder as its percentage. That all about the present experiment. Have a nice learning experience. Thank you.